the modern periodic table in the long form. So the modern periodic table consists of 18 vertical columns. So this is group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8, group 9, group 10, group 11, group 12, group 13, group 14, 15, 16, 17, and finally group 18. So there are 18 groups. Vertical columns of the modern periodic table are called the groups. Now the horizontal rows. Horizontal means this side. Okay, there are 7 horizontal rows which are called periods. So there are 7 periods in the modern periodic table. Period 1. In period 1, if you see, period 1 just consists of 2 elements, that is hydrogen, and right across if you see there's nothing in between, and then we have the helium. Period 2, again you start from here. This part 3 to 12 group if you see is empty. So period 2 starts with lithium, beryllium, and then there is a gap, and then it starts with boron till neon. Then comes period 3, and period 3 is also it happens the same thing as it had happened in case of period 2. Again there is a gap over here, starts with sodium, magnesium, and then there's a gap, and again it begins with aluminium, silicon, phosphorus, sulfur, chlorine, argon. Coming to period 4, period 4 is a long period. There's no gap in between, and the same things are repeated by period 5, 6, and 7. So this is the basic format of the modern periodic table. And then here this comes, this part, the one which is shown below the periodic table, are the lanthanides and actinide series. So we will be discussing more about this series, but this part is called the F block elements. We would be discussing in details about the F block elements. Now, what is the need of the modern periodic table? Because there are 118 elements, and maybe in future many more elements will be discovered, right? So there should be a convenient way to arrange them properly, because we cannot study one single element. It's very tough to study each and every element in details. So that is the reason why the need of modern periodic table took place, because they are arranged in such a way so that in one particular group the elements will share almost similar characteristic properties. For example, if we take group 1, in group 1 we have hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. They have got a lot of things common in them. The most important common factor about these elements of group 1 is they all of them have got valency 1. They have got valency 1, and they all are metals, definitely, except hydrogen. The position of hydrogen, there has been a lot of discussion. So leaving out hydrogen, the rest are all metals, and group 1 is called the alkali metals. Coming to group 2, group 2 is called the alkali earth metals. So what is the similarity among the elements of group 2? In group 2, all the elements will have valency 2. Okay, so this was how they have been arranged. Now, how are the elements arranged in periods? Before I get into periods, how was modern periodic table arranged? Modern periodic table is arranged in the ascending order, increasing order of their atomic number. For example, hydrogen's atomic number is 1, so hydrogen comes first. After that, it is followed by helium. Helium's atomic number is 2. So after hydrogen comes helium. Helium is 2. Then comes lithium. Lithium's atomic number is 3. Then beryllium 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18. I'm counting the atomic numbers of these atoms. Potassium again 19, calcium 20, scandium 21, titanium 22, vanadium 23, chromium 24, followed by the rest and so on. So in the modern periodic table, all the elements are arranged in the increasing order of their atomic number. So let's get back to the groups first. So I have already spoken about group 1. The most important factor about group 1 is in group 1, all the elements will have valency 1. What is valency? The combining capacity of an element, right? To share or accept or donate electrons, right? So if there is 1, 2 or 3 electrons in the outermost shell, it means that they are metals and they are ready to give away electrons, because it will be easier for them to give away electrons, because we already know an atom is highly stable when it completes its doublet or octet rule. Doublet rule means doublet rule is possible only in case of the first shell, that is the K shell. K shell can accommodate only max to max 2 electrons. So if the K shell has completed its doublet rule, doublet means double, then it will be highly stable, which is possible in case of hydrogen. But hydrogen has got 1 electron, so it is highly reactive. But in case of helium, there is only 1 shell and there are 2 electrons. So in case of helium, the doublet rule will be complete and it is highly stable. Whereas in case of other electrons, in case of other shells are followed by L, M, N, O, P, they can accommodate max to max 8 electrons, right? So they would want to have 8 electrons in their outermost shell, but unfortunately they do not have so. For example, sodium, right? Let's take the example of sodium. Sodium's atomic number is 11. So what will be the electronic configuration of sodium? Stop. Okay. Sodium's electronic configuration is 281. So the first shell has 2 electrons, second one has got 8 electrons and the last one has got only 1 electron, because the atomic number of sodium is 11, so 281. Now sodium needs either 7 electrons to complete its octet rule, or it can get rid of this 1 electron and its octet rule will be completed with the configuration 2, 8, because 1 electron it is going to lose. Obviously for sodium it will be much easier to donate this electron, to get rid of this 1 electron rather than gaining 7 electrons. That is the reason sodium will always want to donate its electron rather than gaining electrons. Okay. Similarly, in case of magnesium, it has got 2 electrons in its outermost shell. The atomic number of magnesium is 12. So its electronic configuration would be 2, 8, 2. Its electronic configuration would be 282. Again, in case of sodium, it can either accept 6 electrons to complete its doublet rule, like 6 electrons, and to complete its octet rule, and it will be highly stable, or it can lose these 2 electrons and gain this acquire this electronic configuration of 2, 8, and it is going to be highly stable. Obviously the same thing will happen in case of magnesium. It is much more easier for magnesium to lose 2 electrons rather than to accept 6 electrons. Similarly, the same thing will happen in case of aluminium. Aluminium is 13, so 283. Again, it has got 3 electrons in its outermost shell. If it's aluminium will have 3 electrons in its outermost shell. It can either lose 3 electrons to acquire 283, okay, so to acquire this 28 electronic configuration, or it can accept 5 electrons. So losing 3 electrons would be easier rather than to accept 5 electrons. So in case of aluminium also, it will lose 3 electrons. So if you see the pattern, sodium loses 1 electron, magnesium loses 2 electrons, aluminium loses 3 electrons to attain its highly stable electronic configuration, basically to attain the octet rule. Octet rule means having 8 electrons in its outermost shell. So these are the elements, these are the atoms up to, if it has got up to 3 electrons in its outermost shell, then it can easily lose electrons. But in case of oxygen, let's say, the atomic number of oxygen is 8. So 2, okay. In case of oxygen, the electronic configuration is 2, 6 because the atomic number of oxygen is 8. So 1, 2, 3, 4, 5, 6, 7, 8. Now in case of oxygen, it is much more easier to accept 2 electrons rather than to get rid of 6 electrons. So oxygen will accept 2 electrons. Similarly, let's take the example of fluorine. Fluorine's electronic configuration is 2, 7. Right, because its atomic number is 9. So let's draw the electronic configuration of fluorine. 1, 2, 3, 4, 5, 6 is much more difficult. 1, 2, 3, 4, 5, 6, 7. I'm sorry, yeah. Now it has got 7 electrons in its outermost shell, and it is very, very difficult to, lose 1 by 1 electron 7 times. Rather, for fluorine, it is easier to accept 1 electrons from some other atom, right? So atoms like oxygen, fluorine, they want to accept electrons, and atoms like sodium, aluminium, potassium, they want to donate, they want to lose electrons. So remember one thing, when there are 1, 2 or 3 electrons in its outermost shell, then they want to lose electrons, and this is one of the most important properties of metals. Metals always want to lose electrons, and non-metal starts from 4, like the valency, the ones which has got the valency 4, it's a non-metal. So as now when they have 4 electrons, they want to accept 4 more electrons to complete its doublet rule. In case of oxygen, I have shown you, it want to accept 2 electrons. So when an element want to accept electrons, then this shows the characteristic properties of a non-metal. So this was the need of the modern periodic table. If you see in group 1, except hydrogen, hydrogen is exceptional case, is an exceptional case. All are metals: lithium, sodium, potassium, rubidium, cesium. These are all metals with valency 1. And why they are metals? Because they are ready to lose electrons. They have got valency 1. They want to lose electrons. Valency 1 means they have 1 electron in their outermost shell. In group 2, beryllium, magnesium, calcium, strontium, barium, they all have valency 2. They have got 2 electrons in the outermost shell. They are ready to lose 2 electrons, and hence their valency is 2. Now, let's shift to group 13. Group 13 has got boron, aluminium, gallium, indium, thallium. So they have got 3 electrons in the outermost shells. Means they are ready to lose electrons. They have got only 3 electrons in the outermost shell. Group 13 has got boron, aluminium, gallium, indium, thallium. They all have 3 electrons in the outermost shell. Having 3 electrons in the outermost shell means they are ready to lose electrons, and hence they are metals. Now coming to group 14. In group 14, you have a mixture, rather, because they have got 4 electrons in the outermost shell. So they can either lose 4 electrons or accept 4 electrons. Now coming to group 15. Group 15, nitrogen, phosphorus, arsenic, antimony, they all are non-metals. And why so? I told you one of the most important properties of non-metals are they are ready to accept electrons, and in case of metals they are ready to lose electrons. So they have got 5 electrons in the outermost shell. Group 15 has got 5 electrons in the outermost shell. So they are ready to accept how many electrons in order to complete its octet rule, their octet rule? Obviously 3. So that is why they have valency 3. In case of group 16, the oxygen group, oxygen family, they have got 6 electrons in the outermost shell, which means they need 2 electrons to complete their octet rule. So if they need 2 electrons, which means their valency will be 2. In group 15, they have 5 electrons in their outermost shell, which means they need 3 electrons to complete their octet rule. Therefore, the valency will be 3. In group 17, which is also called the halogen group, which consists of fluorine, chlorine, bromine, iodine, they have got 7 electrons in their outermost shell, so they can readily accept 1 electron and complete their octet rule. So how many electrons do they need? They need only 1 electron to complete their octet rule. They want to accept 1 electron. So since they need 1 electron to complete their stable electronic configuration, hence their valency is 1. So valency basically means the number of electrons that is donated or accepted by the element in order to acquire their octet rule, in order to acquire their highly stable electronic configuration. So in group 1, they want to lose electron. How many electrons? 1 electron. Group 1, the elements of group 1 want to lose 1 electron to complete its octet rule, valency 1. To complete a group 2, in order to complete their octet rule, they want to lose 2 electrons. Therefore, the valency 2. 3 to 12 transition elements, we would be discussing later about it. Now group 13, they have 3 electrons in their outermost shell. In order to complete their octet rule, they want to lose 3 electrons and therefore the valency is 3. In group number 14, they have got 4 electrons in their outermost shell. So they want to either lose 4 electrons or accept 4 electrons. Therefore, the valency is 4. Group 15, they have got 5 electrons in the outermost shell. So in order to complete their octet rule, they want to accept 3 electrons. Therefore, the valency is 3. Group 16, valency 2 because they want to accept 2 electrons. Group 17, they want to accept 1 electron and therefore the valency is 1. In case of the halogen group, group number 17. Group number 18 has got 8 electrons. In case of helium, it is only 2 electrons and the rest will have 8 electrons in their outermost shell. Helium has got only K shell and therefore its doublet rule will be completed. In case of helium, the rest will follow the octet rule and their doublet as well as octet rule are complete, and therefore group number 18 elements are very highly stable, and therefore the name inert gases, noble gases have been these names have been given to the group number 18 elements because they are highly stable. That is why they neither want to gain electrons nor they would want to accept electrons. They are already stable. They are not interested to involve with any other atom, with any other thing, and hence the name inert gas or noble gases. They are highly stable, so they have got 0 valency. So valency can never exceed 4. So how do we know? So let's start from here. Valency 1, valency 1, valency 2, valency 3, 4, 5, wrong. It will be 3. 2, 1, 0. So basically 1, 2, 3, 4, 3, 2, 1, 0. So group 1, valency 1. Group 2, valency 2. Group 13, valency 3. Group 14, valency 4. Group 15, valency 3. Group 16, valency 2. Group 17, valency 1. Group number 18, valency 0. So basically the series is just like 1, 2, 3, 4, 3, 2, 1, 0. 1, 2, 3, 4, 3, 2, 1, 0. So this is how we also find out the valencies. Now, group 1 is known as the alkali metals. Group 1 has got valency 1. Group 2 has got the valency 2 and they are called alkali earth metals. Group 3 to 12 are called transition elements because they have their two outermost shells incomplete. So group 3 to 12 are known as transition elements. Group 13 is called the boron family. As you can see, boron is the first member of the group 13. Group 14 is also called the carbon family, as carbon is the first member of the group 14. Group 15 is called the nitrogen family, as nitrogen is the first member of this group. Group 16 is called the oxygen family, as oxygen is the first member of this group. Group 17 is called the halogen family, halogen group, as they form salts with metals. So that is why they are called halogen groups. And group 18 is known as the noble gas because they are highly stable, they have zero valency, they do not react. Thank you very much.